Assalamu alaikum and hi, my name is Akhtar Nasir Sharif, and in this video I will present the assignment for Communication Principles by Group 7 titled M-ary Phase Shift Keying, or MPSK in short. Joining me is Muhammad Uman Haris bin Roslan, Ahmad Ajwad bin Azmi, and Muhammad Izami Ashraf bin Rosaiddin. Starting from introduction, PSK or phase shift keying is a widely utilized modulation technique in radio communication applications around the world. So basically the idea behind PSK modulation is to shift the carrier signal's phase for each binary bit. So the amount of phase shift is determined by the bit value. The M in M-ary PSK stands for the various degrees of phase shifts in that PSK. So the degree of phase shift can be multiple according to the M or modulation. PSK also outperforms FSK in terms of efficiency. As a result of that, it is more noise resistant than ASK or FSK. However, a frequency multiplier is employed to maximize phase modulation index. So it is kind of significant disadvantage to the system. In theory, in phase shift keying modulation or PSK modulation, phase of carrier is changed according to the digital data. It is a digital modulation technique. It is common to be used in broadcast video system, aircraft, and satellite systems. We can achieve bandwidth efficiency when we represent each signal element to map more than one bit. In binary PSK modulation, digital data of 1 and 0 is represented by 180-degree phase change, while in quadrature PSK by phase shift of 90-degree, here 2 bits are mapped on each signal. In multi-level PSK, more than 2 bits are mapped using different phase angles. For example, 8 PSK, there are 8 different phase angles used to represent bits, which are 3 bits. So in the next slide shows you will see the constellations of 8 PSK signal. In addition, note that M equals to 2 in the power of n. So hence why when the modulation level is 8, the number of bit is 3. The same rules apply to binary when the number of M is 2, the number of bit is 1, while in quadrature the number of M is 4, the number of bit is 2. So what we try to explain is in a 360 degrees of phase, the phase shift key changes according to the modulation level. For example, in binary, the phase change is 180 degrees because 360 degrees is divided by 2, while in quadrature it equals to 4. Therefore, 360 degrees divided by 4 will be a phase shift of 90 degrees each. The same as 8 or 16 or so on modulation level. So for example, like in 8 PSK, 360 degrees divided by 8 will be 45-degree phase shift each. So now let's see. This is the constellation diagram of 8 PSK. You can see that the phase is 360 degrees and it is divided by 8. So which is why each is 45 degrees. Continuing with the theory, the signal representation which uses the combination of 2 or more bits to represent a single symbol is known as M-ary or multi-level signaling scheme. So multi-level can be considered to start from 4 levels, then 8, 16, and so on. Figures below showed how different number of modulation levels affect the output waveform. As you can see, the top we have the binary ASK, while the bottom we have multi-ASK. In the binary, you can see there are 2 levels, 0 and 1, and each symbol has only 1 bit compared to multi-ASK. In 4 levels, the levels start from 0, 0 up to 1, 1, and each symbol has 2 bits. And another thing, the multi-ASK took 5 steps to create a waveform that the binary created, which took 10 steps. Next, we have the flowchart for M-ary PSK modulation and demodulation. Starting from initializing the value of filter span, roll-off factor, and samples /second. Second, we take the value of M from user to perform the M-ary PSK. Then we generate bits and symbol and phase offset by using the value of M. Next, we create filter coefficient using RCOS design function. Following that, we generate a random signal of size M and perform M-ary PSK emulation. From that, we filter the modulated data. Then we calculate signal to noise ratio for the M-ary PSK signal. After that, we create a channel and add AWG or additive with Gaussian noise to the transmitted signal. We will receive and apply RRC filtering to the received signal. Then we perform the demodulation on the signal. Finally, we plot the constellation diagram, scatter plot, and eye pattern of transmitted and received signal. The end. Moving on to the results, let's start with the MATLAB coding. In the first part, we have the message signal. We declared the number of symbol as n equals to 10, and the modulation level as m equals to 8. As for the data input, we used the command randy to randomize the data input, which the data has been generated with 1 times n column vector of uniformly distributed random integers from this sample interval. Then we use the command psk mode to modulate the input data. In the second section, we have the AWGN or additive white Gaussian noise for constellation points. We set the signal to noise ratio as 20. Basically, this coding line is used to add white Gaussian noise to the input signal, while at the same time measure its power. Then we set the minimum carrier frequency as 1 kilobit. This part is basically the time duration used in the signal generation. Then in the third section, there's a transmitted signal waveform. In order to generate a transmitted signal, the L must equal to 1 or to the max length of the data. Then it will proceed to the formula of real and imaginary signal, which will generate the final signal of transmitted waveform. After that, in the fourth section is for received signal waveform. It's a bit similar to the previous command line, except that AWGN is added to create a noise which mimics random processes of natural occurrence. Finally, the last section is for waveforms of the signal. So basically, the usual commands such as subplots, grid, y limit, and x limit are titled to create the final output waveform. Here we have the results for the output waveform. First, we have the message signal. As you can see, based on the theory that I just explained, the modulation level is divided by 8 from 0 to 7, or in another way, from 0, 0, 0 up to 1, 1, 1. So the correct way to read the message signal is each symbol is supposed to have 3 bits from here: 0, 1, 0, 1, 0, 0, 0, 0, 1 for 1, 1, 0, 1, 0 for 2, 1, 1, 0 for 6, 1, 1, 1 for 7, 1, 0, 0 for 4, 1, 1, 1 for 7, and 1, 0, 1 for 5. Then we have the transmitted signal. This part is the modulation of this part. In a phase, there are 360 degrees. So for a level 8 PSK, 360 degrees divided by 8. So for each phase shift is equal to 45 degrees. So how to read the transmitted signal is from here to here. You can see that there is increase by 2 levels. So 2 times 45 degrees equal to 90 degrees. So from here to here, you can see that there is signal phase shift backwards by 90 degrees. Then you can see that from here to here, there is a decrease by 3. 3 times 45 equals to 135 degrees. Therefore, from here to here, the signal moves forwards by 135 degrees, and so forth. Then we have the 8 PSK received signal with AWGN or additive white Gaussian noise. It is basically this a similar modulation waveform as the transmitted signal, except the waveform is kind of blurry because there is noise with it. Now into the discussion. The coding was separated into 3 parts. The first part is message signal. The value of message signal was generated randomly. The message signal waveform is a square wave that consists of multiple amplitude representing from 0 to 7 in binary, which is 000, 001, 010, 011, 100, 101, 101, 110, and 111, respectively, because the modulation order is 8, which is 3 bits per symbol. So M equals to 8 levels. In the second part is the modulated signal. The line above mean the input signal, which is the data, was modulated by using the phase shift keying with modulation order M and the initial phase of 0. The waveform is shown in result as the second waveform. The modulated waveform was phase shifted based on the different amplitude of the message signal. Because the modulation order is 8, the phase shift difference between the bits is 45 degrees based on the constellation mapping of 8 PSK. Finally, the third coding is for the received modulated signal. The waveform of the received signal is the same with modulated signal, but with the addition of Gaussian noise to replicate the noise that happened to the signal when it was transmitted. The coding line above mean that the added white Gaussian noise was set to the vector signal and accepts an input signal power value in decibandwidth. The signal power was set as measured to have the function measure the power of transmitted signal before adding noise. In conclusion, the phase of the carrier is modified according to the digital data in PSK modulation. The first waveform is the message signal waveform, which is a square wave that consists of multiple amplitude representing from 0 to 7 in binary. The second waveform is the modulated signal waveform, which was phase shifted based on the different amplitude of the message signal. The third waveform is the received modulated signal with the addition of a Gaussian noise. Based on first and second waveform, the pulse width and amplitude of the message signal corresponds with the modulated signal phase shift. This confirms that the coding is functioning properly. This is all from us. Thank you very much and goodbye.